Assalamualaikum.
وعليكم السلام ورحمة الله.
Okay, so welcome to the class of microwave engineering.
Excuse me, Sarji.
GG. Yes. Yes, I am listening. What do you want to say? Can you people hear me clearly?
Yes, sir.
Yes, sir.
Okay. Okay, so let's continue with our discussion about Smith chart. So today we are going to find out how to use Smith chart to solve some problem. So as I pointed out in my previous lecture that the utility of Smith chart is that you can solve any problem graphically without making use of analytical equations. So last time I explained in detail how Smith chart was developed by Peter Smith way back in 1939. And today we are going to find out how to make use of that chart if you are solving any transmission line problem. Okay. So what we, just to recapture, in the last lecture, we found that Smith chart is basically a graph that is plotted in the gamma plane. So let me just refresh your memory. So it is a chart that is drawn on gamma plane. And what it consists of? It consists of resistive circles and reactive circles. So if I draw a rough Smith chart, so if this is a gamma plane, and we know that in the gamma plane, the area that is of use to us is that unit area, so unit circle. So if I draw so this is the unit circle. So what we saw last time is that Smith chart consists of a number of resistive circles, which are plotted like this. And it consists of some the reactive circles. And because somehow some portion of the reactive circle is outside of the unit circle, so I'm just drawing the portion of the circles which are within the unit circle. So this is what I meant by saying that it consists of resistive circle and reactive circles. So the red ones are resistive circles and the blue ones are reactive circles. So with this knowledge, now let's consider a problem that we are going to solve with the help of Smith chart. So let's consider an example. So example is a load impedance of 40 plus J70 ohm terminates a 100 ohm transmission line. That is 0.3 lambda long. And we are asked to find out the following quantities. Find the reflection coefficient at the load, the reflection coefficient at the input to the line, the input impedance, the standing wave ratio on the line, and the return loss. So you can see we need to find out a number of parameters or number of unknowns within this problem. So the first thing that we need to find out is this one, the reflection coefficient at the load. Secondly, we need to find out the reflection coefficient at the input to the line. Third thing, we need to find out the input impedance. The fourth one is the standing wave ratio on the line. And the fifth one is the return loss. So these are 5 quantities or 5 unknowns that we need to find out for this problem. And if you represent the information that is given to you in this example in the form of a figure. So what we have is we have a transmission line. Load impedance is this one. This is the 100 ohm transmission line. So it means this is the characteristic impedance that is given to you. And you are also given that the length of transmission line is 0.3 lambda. So if I represent this information in a graphical form, so I will draw transmission line. This is how we represent transmission line, by drawing these two parallel horizontal lines. So the right side is usually used for connection to the load. So it means we have ZL equal to 40 plus J70 ohm. Transmission line Z0 is given to you, it is 100 ohm. And the length of transmission line, let me represent the length with symbol L, small l, and then 0.3 lambda. So this end is the input. So with this information, that is transmission line, having characteristic impedance equal to 100 ohm, having length equal to 0.3 lambda ohm, and connected with this load, we need to find out these 5 unknown quantities. Now, if you don't use Smith chart, of course, you can solve this problem, and by making use of equations that we have covered within our last 2 lectures, you can solve this problem analytically without using Smith chart. But right now, we are more interested in solving this problem with the help of Smith chart. Okay, so let's find out how you are going to use Smith chart to find the 5 unknown quantities. So the first thing, if you remember, I mentioned this thing when I was talking about the Smith chart, is that Smith chart is used only for normalized quantities. Smith chart is used only for normalized quantities. So the first thing, whenever you start solving any problem using Smith chart, is to normalize the quantities. So it means this load which is given to us is the actual load, and we need to normalize this load. Okay. So how we will normalize it? We have also covered this part as well, that the transmission line characteristic impedance is going to be used as a normalization constant. Okay. So how you will normalize it? So normalize it. Okay. So how you will normalize it? What you will do? You will divide the actual ZL by Z naught. And this will give you normalized load, and we usually use this symbol for normalized load, that is small zl and dash. So we will get the normalized value, that is 40 plus j70 divided by 100. So zl dash is going to be equal to the normalized real part is zero point 0.4, and the normalized imaginary part or reactive part is 0.7. So this is our normalized load impedance that we are going to use on the Smith chart. So now we need to find out what is the location of this normalized load. Okay, so what you need to do now is, so I'm just making a note of the steps. So the first step that you did is normalize the given ZL. After doing this step, what we are going to do next? Locate normalized So normalize the given ZL to get ZL dash, and then locate normalized ZL dash on the Smith chart. On the Smith chart. So let me open the Smith chart in front of you, and what we are going to do is we are going to find out where is the location of this normalized load. It's 0.4. So the real part or resistive circle is of 0.4 ohm, and the reactive or the imaginary part is 0.7. So you need to find out where is this circle on the Smith chart and where is this circle on the Smith chart. So this is the Smith chart that you are going to use, and we are going to locate ZL dash 0.4 plus J 0.7. So first of all, let me find out where is 0.4 resistive circle. So we already know the location of the resistive circle. So you need to find out where is the resistive circle. So you can see, let me highlight it. This is the axis that I mentioned last time, that the scale reading given here on this horizontal line is telling you that which particular circle, resistive circle is. For example, my goal is to find out this circle, 0.4. So where is 0.4? 0.4 is written right over here. Okay, so you need to mark this circle, or you need to find out where is this circle. So now right in front of you, this is the resistive circle. Let me draw on top of it so that you can clearly see. So if you can see, this is the point 4 circle, point 4 circle. Let me stop at which it is easier for you. So this is the circle. You can see that this is the point 4 resistive circle. I'm just drawing on top of it just to give you an idea that this is the circle that you need to look at. Okay. Now you have identified where is the point 4 resistive circle. Okay, I'm not drawing the complete circle. Okay, you can clearly see that this is the whole circle. If you want to completely plot it, this is the whole circle that is representing point 4. Okay, and then we need to find out where is this imaginary circle or reactive circle, and reactive circle is 0.7, and you can see it's positive circle is positive value, so we need to be focusing only on the top portion of the Smith chart. Okay, so you can find out where is again I need to zoom this, so let me so where is 0.7 reactive circle. So this is the scale. If you remember, I've talked about this scale before. This scale reading that I am highlighting, you are going to use this scale to identify the reactive circle. So you need to find out where is 0.7. So this is 0.7. So now it's easier for me to highlight it. So this is the circle that you need to look at. And all you need to do is find out where the two circles are intersecting. Which circle? The 0.4 resistive circle and 0.7 reactive circle. So right now I am just highlighting. Again, when you are going to solve this problem on the Smith chart, you are not going to do this thing. I'm just doing this for explanation purposes. Okay. All you need to do is visually identify where is the 0.7 circle and then where is the 0.4 resistive circle. This is the 0.4 resistive circle that I highlighted before as well. So let me do it again. And you can clearly see that the two circles, they will intersect at one point. They will intersect at one. So I'm highlighting just for your information purposes. Otherwise, in actual cases, you are not going to do this thing. All you need to do is visually find out the intersection point. So now I am just marking the point at which they are going to intersect. So what was the load value? Normalized load value was 0.4 plus J 0.7 ohm. So what I did, I identified the 0.4 resistive circle, I identified the 0.7 reactive circle, and then I find out where these two circles are intersecting on the Smith chart, and this is the intersection point, and this is going to be the location of ZL dash. So now I can mark this point at this is ZL dash. So the normalized load that is given to us in the problem or in the example, its location on the Smith chart is this one. This is the first step that you need to do. Okay, and you can use, again, this is the general method. Whenever you are asked to locate any given impedance on the Smith chart, this is what you are going to do. You need to find out the intersection of the resistive circle and the reactive circle, and the intersection point is going to be the location of the Smith chart. So if I go back to the actual discussion that we are having, so what we have done is we have normalized the load impedance, and then we have located the normalized impedance on the Smith chart. So we have completed this step. Now what we are going to do is, so if you look at the unknowns that we need to find out, the first unknown is find the reflection coefficient at the load. Okay, so just focus on the first unknown quantity, the reflection coefficient at the load. So what we need to do is we need to find out how much is the reflection coefficient at this point. So let me call this as gamma load. This is the first parameter or unknown that I need to find out. So how to find this using Smith chart? Okay, so let me go back to the Smith chart. Let me mark that point. So now you can clearly see that in actual cases, what you will do, you are going to visually do this. So I can easily identify the previously marked point. This is the point. This is the intersection of point 4 resistive circle and point 7. So this is ZL dash. Now before I find out the parameter that I want to find out, that is how much is the reflection coefficient at the load. Uh, let me identify the location of some common load values. Okay, as an example, let's do this, and then we will come to the actual example. If it's given to you that ZL is some kind of a real load, so it has only real part. As an example, let's consider that ZL is given to you and its value is 100 ohm. So this is, you can clearly see this is an example of a real load. So where will be the location of this impedance on the Smith chart? So as before, the first thing you need to do is to normalize any given load. So for this particular discussion, I'm going to assume that Z naught is 100 ohm. Okay, this is just for example. Okay, Z naught can be 50 ohm, it can be 75 ohm or 100 ohm. So what is going to be the normalized load impedance? ZL dash will be equal to 1. So where is this real load located? So all real loads, they will be on this line, this horizontal line. Because if you are on this line, it means imaginary part is equal to 0. Okay, this horizontal line means it is only valid for real load. And right now we are dealing with the real load. All you need to do is find out where is this circle, resistive circle equal to 1. And you can clearly see this is the resistive circle, which is equal to 1. And because imaginary part is 0, so it means the location of this this load will be at this point. So let me, to be more specific, let me call this example as A. So I can say that this is A. So no matter what is the value of the real load, what is the value of the load, if it is a real load, it will always be on this horizontal line. Let's consider another example. Let's consider an example that we have ZL actual load is equal to, let's say, 200 ohm. And you can see it is still a real load, purely real load. So what will be the location of this load on the Smith chart? Again, I will going to normalize it. So our normalization constant is 100 ohm. So in this case, the normalized value of load will be equal to 2 ohm. Let me call this as example B. So where is this point on the Smith chart? We need to find out the point where we have 2 over here. So let's see where is 2. So it's 2 right over here. So this point is going to represent this value. So now it's these 2 examples are enough to give you the idea that whenever you are dealing with a purely resistive load, it will be somewhere on this horizontal line, depending upon what is the actual value. So all resistive loads will be on this horizontal line. Okay. Now there are 2 extreme values that I want to consider. Is, let's assume that you are dealing with a short circuit load. Short circuit load. So let's consider another possibility that ZL L is equal to 0 ohm. And it means we are talking about short circuit load. So of course, normalized value will also be equal to 0. 0 divided by 100 is 0. So what is the location of this point? So let me call this as point C. So you can see that this is the values from, if you move towards right, this is 1, 1.1, 1.2, 1.3. So it is increasing. But if you go towards left side, it is 1, 0.9, 0.8, 0.7, 0.5. So if you are right at this point, let me mark this point, this one. If you are at this point, so it means the value is 0. So it means this point I'm going to call it point C. So this is a very common point that we will use many times in microwave engineering. So make sure that you remember that ZL dash equal to 0, which is a short circuit load. So short circuit load location on the Smith chart is is at the extreme left side, which is this point, which I have clearly marked. Similarly, if you are dealing with an open circuit load, so now if ZL is almost infinity, so this is now open circuit load. So ZL dash will also be approaching to infinity. So normalized, where is this point? So you can see the values are increasing towards the right. So this is 2, this is, you can see it is 3, 4, 10, 20, 50. And then this point, right, which is at the extreme right of the Smith chart. So let me call this as point D. So this point represent an open circuit load. So this point is going to be the location of any open circuit load. Okay. So now you have an idea that whenever you are dealing with real impedances starting from 0 ohm to infinity ohm, they will be anywhere on this horizontal line. Okay. Similarly, let's consider another possibility. If you are dealing with purely imaginary load, so let's consider that the load impedance is given to you and it is equal to, J 100 ohm. So it is a purely imaginary load. So where is the location of this impedance on the Smith chart? So first of all, we will normalize it. So ZL dash, because I'm using this case, so ZL dash will be simply J. So where is this value on the Smith chart? So I have mentioned this point before as well, but let me mention it again. If you are dealing with purely imaginary loads, no matter what is the value of that impedance, if it is a purely imaginary load, imaginary loads will always be on the outer boundary of this Smith chart. And right now I am highlighting which particular circle I am talking about. So all imaginary loads will be anywhere on this outermost circle of Smith chart. So for this example, it is equal to 1J. Okay. So where is this reactive circle for this value? So you can clearly see this is the circle that I'm talking about. It's written 1. So it means this is the point. So let me call this example as point E. So where is this on the Smith chart? This point is point E. Similarly, consider another example. ZL equal to 200, J 200 ohm. So ZL dash will become J2 ohm. And let me call this example as F. So where is this value? This value is right at this point. This is point F. And you can consider any example of purely reactive or purely imaginary load, and you will find out that its location on the Smith chart will be anywhere on this circle. Of course, I'm considering positive values, but we know that reactance can be negative as well. So you may be having ZL equal to minus J100, minus J300, minus J500. Then it will be at the bottom of the Smith chart. Okay. So it will be somewhere on this circle. The point is all imaginary loads are on the outermost circle. So now we can consider all possibilities. So our load can be purely resistive or purely real load, or load can be purely imaginary load or purely reactive load, or general cases our load is a complex load. And the example that I was solving is an example of complex load, because ZL is equal to 40 plus J70. So it has a real part as well as imaginary part. So if I summarize this whole discussion, the possible location of load, impedance, or any impedance, again, because I'm talking in terms of load impedance, but this discussion is valid for any impedance. If you want to find out the location or position of any impedance on the Smith chart, so now you have this general concept that if load is resistive, it will be anywhere on this horizontal line. It will be anywhere on this horizontal line. Okay. And if load is purely imaginary, then it will be anywhere on this outermost circle. It can be anywhere on this outermost circle if it is purely imaginary. And if it is complex load, so it will be either in this region or it can be anywhere in this region, depending upon whether you are dealing with an inductive load or with a capacitive load. If load is inductive, it means it has some real part and some imaginary part, which is positive. So it will be somewhere over here, like this example, which I'm solving. You can see this value, let me write it down. This value is equal to 0.4 plus J0.7. So it is complex load. It has a real part as well as imaginary part. And because imaginary part is positive, so it is an inductive load. So you can see that it is is in this region. You can consider any complex load, but if it is an inductive load, so it will be anywhere within this area. It will not be exactly on this line, horizontal line. It will not be exactly on this outermost circle. It will be in between these two lines, this straight line, and you can say this curved line. And if it is a complex load, but the imaginary part is negative, which means it is a capacitive load, then it will be anywhere in the bottom half of the Smith chart. Okay. So now we have this general information. So uh, let me summarize this discussion. That these are this is the outermost circle, and this is the horizontal line. So what I have shown you, what I have concluded from this whole discussion is that this line is for all real impedances. Okay, and this outermost is for all imaginary impedances. And this area and this area is for all possible complex impedances. Let me add all purely imaginary impedances. And in addition to that, you also need to remember these 2 points, this point and this point. This point is for short circuit impedances, and this point is for open circuit impedances. So these 2 points are also important during solution of many problems. Okay. So with this information, let me come back to the example that we are trying to solve with the help of Smith chart. So the first parameter, first unknown that I'm looking for is to find out the reflection coefficient at the load, this one. So how to find this parameter with the help of Smith chart? So after locating the normalized load impedance, what we are going to do now is okay, every time I open Smith chart, everything gets deleted. So let me draw it again. So this is the location of the load impedance that we have identified. This is ZL dash. So once you know the position or the location of the impedance on the Smith chart, then it becomes easier for us to find number of unknown parameters. So how to find out the reflection coefficient? So the first parameter that we need to find out is reflection coefficient at the load. The reflection coefficient is a complex quantity, so we need to find two things. We need to find out how much is the magnitude of the reflection coefficient. And we also need to find out how much is the phase of the reflection coefficient. So these are two unknowns that we need to find out. Okay. Let me talk about this in the next session because the 40 minutes time limit is about to finish. So let me continue this discussion in the next session.